Welcome to VTU Physics. In this video, we are trying to understand the topic called laser. Before we are going to jump into the syllabus, let us start to understand what is laser stands for. So, laser means it's a light amplification by stimulated emission of radiation. So, try to understand word by word. So, starting with light. What is light? Light is the form of energy. Now, what we are going to use it, we are going to amplify it by a amplification process. What will happen in the amplification? We are increasing the amplitude of a light. Nothing but we are increasing the energy. Once we got increased energy, what will happen? We will get stimulated emission. What is the meaning of stimulated emission? There is a transition of electron. Once we got a transition of electron, after that we are going to get a radiation. What does it mean? It means that energy comes from a source and travels through space at the speed of a light. By combining all these processes, we are going to get ultimately one word, that is laser. Next topic is what is the characteristics of the laser beam. There are mainly four characteristics. One is laser beams are highly monochromatic. That means laser light are single wavelength or color of a light is single. So that means you will get laser light in one color, that is in red or in green. That is the first characteristics of the laser light. In second characteristics, you can say laser beams are highly coherent. That means light waves are in phase with another and maintain a consistent phase relationship over a longer distance. That means in the case of laser beam, crust and trough are in single phase. They continue or they maintain same consistent phase relationship over a longer distance. But in the case of normal light, there is no any kind of relation, as you can see in this diagram. Let us see the next characteristics of the laser beam. Laser beams are highly directional. That means laser lights are focused into a narrow beam with a very little divergence. Next characteristics of a laser beam is laser beams are highly intense. That means laser light contain a large amount of energy in a very small area. These are the main four characteristics of a laser. So, in the next topic, we are trying to understand the interaction of radiation with the matter. Here, we are going to see three main interactions. One is induced absorption, second one is spontaneous emission, third one is stimulated emission. Let us see one by one. First one, induced absorption. Here, we are trying to understand what will happen when radiation interact with the matter. For that, we need two energy state, E1 and E2, or lower state and higher state, or lower state or excited state. In the process of absorption, firstly, we need to specify the electron position. In the case of absorption, electron position is in lower state. Now, once the absorption, what kind of absorption? Energy is absorbed by electron, then this electron will absorb it, and due to this absorption, electrons start to move towards the excited state. This entire process, we call it as induced absorption. In the next process, where we can say it as a spontaneous emission. In this process, electron position already exists in the excited state. Because of extra energy, this electron loses its stability and is unable to handle that much energy in the excited state, and it will not be enabled to stay for a longer period. Without any stimulation, it comes back to the ground state energy level. While it's coming back to the ground state energy level, it emits all the radiation, whatever it stores before when it is present in the excited state. This entire process, we call it as spontaneous emission. Lastly, we'll see what will happen in the stimulated emission. In this process, electron position already in excited state. So now we need to stimulate by sending an energy, and due to this stimulation, electrons come back to the ground state energy level. While it's coming back to the ground state energy level, it loses its energy. And there are two light waves are producing. One is for stimulated energy, another one is for the electron which is holds before when it is present in the excited state. And ultimately, we will get the single color light, nothing but monochromatic laser light. Once you understand what will happen when radiation interacts with the matter, now let us understand the minimum condition required to get a laser light. Here, we need to maintain two important conditions. One is metastable state, another one is population inversion. So let us start with metastable state. What is metastable state? It is the state which is present in between. One is excited state, another one is ground state. This state we call it as metastable state. Second condition is population inversion. In this process, or this is a kind of situation where number of electron present in excited state is more compared to ground state. This situation or this condition, we call it as population inversion. These are the two important conditions we must maintain to get a laser light. We are going to understand, or we are going to derive an equation for energy density, nothing but Einstein A and B coefficient. This concept is very important as a exam point of view. This concept you may expect for 8 to 10 marks in semester exam as well as in IA also. So let us see and derive the equation for energy. We need to say that E1 is an ground state energy level, E2 is an excited state energy level. In E1 state, we have N1 number of electron. In E2 state, we have N2 number of electron. Now, let us consider three minimum cases. One is induced absorption, second one is spontaneous emission, third one is stimulated emission. All these three explanations will be converted in the form of equation. So, starting with induced absorption. In this case, electron initially present in ground state is nothing but E1 state. So once it's absorbed by some energy, then this electron will gain that energy and it will move towards E2 level, nothing but excited level. So this process we call it as absorption. So how many number of electron is going to E2 level, how much energy will be absorbed? For that, we can write it as rate of absorption is directly proportional to N1 number of electron which is present in E1 state. Okay. Now, take this sign by considering one constant which we call it as Einstein coefficient. In the case of absorption, we can write the above equation like this: rate of absorption is equals to, by considering one constant value, that is B for absorption, and there is a transition from E1 to E2. That's why we can write it as 1 and 2. How many number of electrons going to transition? N1 number of electrons. We write it as N1. To make a transition, energy required? Yes, energy is required. That's why we can write it as E nu. Now we got the equation for rate of absorption. Similarly, in the case of spontaneous emission. So, initially electron present in excited state, because the continuation process of induced absorption is nothing but spontaneous emission. So, electron present in excited state where that extra energy is also already is present inside the electron. So due to this electron is unstable now, and without any stimulation it comes back to the ground state energy level by emitting some radiation. Okay, so convert this explanation into the equation form, then we can write it as rate of spontaneous emission is directly proportional to N2. That means E2 level we have N2 number of electron. For that, take out this symbol by considering one constant value, that is Einstein coefficient A in the case of spontaneous emission. So write the above equation like this: rate of spontaneous emission is equals to A for Einstein coefficient. The transition of electron is going to take place from E2 to E1. That's why we can write it as 2, 1. How many number of electrons? N2 number of electrons. That's why we can write it as N2. To make a transition from E2 to E1, does it require energy? No, it doesn't require energy. That means that's it for rate of spontaneous emission. Okay, so let us see the next slide where there is a stimulated emission. Now, in this case, once again electron present in E2 level. Okay, so in this case, we need to stimulate this electron to make a transition from higher state to lower state. While it's coming back to lower state, that means E2 to E1, this electron emits all the radiation whatever it has. So that means we will get laser light. Okay, now convert this explanation into an equation. That means rate of stimulated emission is directly proportional to N2. Now take this symbol by considering one constant value, that is nothing but Einstein coefficient B. So rate of stimulated emission is equals to P. Where is the transition of electron? E2 to E1. So 2, 1. How many number of electron? N2 number of electrons. So that's why N2. To make a transition, energy required? Yes, energy required. That means E nu. So we got 3 equation. Okay. Now let us consider one important condition. What does it say? Here we need to maintain, or we need to say, at thermal equilibrium condition. In thermal equilibrium condition, that means we are not providing any kind of energy except room temperature, and that too constant temperature. Okay, in this process, how much absorption is going to take place? That much emission will be takes place. Now write the equation where rate of absorption is equals to the addition of two emission, that is rate of spontaneous emission plus rate of stimulated emission. We have equation for this. Just write down that equation. For rate of absorption, we have B12 N1 E nu is equals to, for rate of spontaneous emission, A21 N2 plus, for rate of stimulated emission, B21 N2 into E nu. Now take it as equation number 1. In equation number 1, this side and this side we have similar notation. Just take it outside and write it in one place. We can write it as B. Instead of that, we can directly write E nu is a common B12 into N1 minus B21 into N2 is equals to A21 into N2. Okay. So here we are trying to find out the energy density equation. This symbol indicates the energy density equation. So that's why we will send this equation to this side, that nothing but denominator side. So that means we can write it as E nu is equals to A21 into N2 divided by P12 into N1 minus P21 into N2. Okay. So we need to cancel out N2, N2, but we can't do directly. So for that, we can write this equation like this. A21 into N2 by B21 into N2 into 1 by B12 into N1 divided by B21 into N2 minus 1. Okay. So here we have B12 for rate of absorption. Now B21 for rate of stimulated emission. At the thermal equilibrium condition, both are equal to each other. That means how much absorption is there, that much emission is there. So that's why we can write it as B12 is equals to B21. Okay. Now we have N1 by N2. In the case of population inversion, we have one equation that we call it as Boltzmann distribution law, that is N2 by N1 is equals to e raised to minus h nu by kt. Okay. But in above equation, we have N1 by N2. That means just send this equation in denominator. Nothing but if we take into the numerator, this negative sign will be converted in the form of positive sign. Then the equation will return it as e raised to h nu by kt. Okay. We got it. We just substitute here in this equation, and ultimately the equation which we are getting, E nu is equals to A21 by B21, because here N2 will get cancelled. That's why we can write it as E21 B21 into 1 by e raised to h nu by kt minus 1. We got one equation. Okay. This is the important equation. By considering Planck's radiation law says E nu is equals to 8 pi h nu cube divided by c cube into 1 by e raised to h nu by kt minus 1. Take this equation number 2 and equation number 3. Now compare these two equation number 2 and equation number 3. What we will get? E nu will get cancelled. This side of the equation and this side of the equation will get cancelled. Remaining is a to 1 divided by b to 1 is equals to 8 pi h nu cube by c cube. So this means this much energy is required to make a transition for an electron. Now write down the simplified version of the equation number 2 by neglecting 2 1 2 1. So ultimately the equation we can write it as E nu is equals to A by B into 1 by e raised to h nu by kt minus 1. This is the equation which we call it as energy density equation. I hope you got to know whatever I tried to explain it here. The semiconductor laser or diode laser, also we call it as gallium arsenide laser. In this construction, we need to consider p-type semiconductor, which is heavily doped, n-type semiconductor, which is also heavily doped. Put together, we call it as diode. Now, the diode which is used here is in cube form. That means the dimension of this cube is about 0.4 mm. The depletion region, which we also call it as active region, the thickness of depletion region is about 0.1 micrometer, lies horizontally as shown in the figure. Now, the current is passed through the ohmic contact provided to the top and bottom surfaces. The front and back face are polished, made highly parallel to each other to have a laser cavity. Other two faces are roughened to avoid laser leakage. This is about construction of a laser diode. Once you understand the construction of semiconductor laser or diode laser, we'll try to understand the working of semiconductor laser. For that, we need energy level diagram. As you can see here, one side there is a p-type semiconductor, another side there is a n-type semiconductor. By joining this, there is a junction or depletion region is there. Now, because of diode is in forward bias, by using external source, there is electrons and holes flow across the junction. Hence, the current flow through the diode. When a hole meets electron, it recombines with electron by emitting a photon. Okay, what will happen for initial voltage or for a low current? Then there is a only few electron is going to recombine with few holes. Due to this reason, the spontaneous emission will be seen. Due to this reason, the entire setup work as an LED, light emitting diode. Once the threshold voltage reaches or once we achieve high current, then there will be a number of electron recombining with number of holes are more. Due to this reason, there will be a stimulated emission takes place. So due to this reason, finally we are going to get a laser light. This is the working of a semiconductor laser. Once you understand this construction and working of a semiconductor laser, let us see applications of laser. In that, we will start first with laser barcode reader. As you can see here, this is the construction of a laser barcode reader, which consists of one is laser source, second one is mirror, third one is photo detector, and fourth one is barcode itself. So, how it works? As you can see, the laser source produces a laser light, falls on a mirror, and that mirror reflects back that laser light on a barcode. So, the barcode is a combination of white and black strip. So, wherever there is a black strip, light will be absorbed. Wherever the white strip will be there, the light will be reflected back. When the light, nothing but laser light, reflected back, that reflected light ray is detected by a photo detector, as you can see in this animation. So, like this, the laser barcode reader works. What will happen once the reflected light rays detected by a detector, as you can see in this diagram? So all the data which is there in that barcode will be read it and show on a monitor. This is how the construction and working of a laser barcode reader. Let us see the second application, that is laser printer. As you can see in this diagram, here we need laser as a source, mirror to reflect that laser light, drum to get that reflected light on the photosensitive material. Tuner is used to dispense fine particle on a drum. Last but not the least, fusing section to produce heat, and all these things are going to happen on a white sheet of paper. This is the construction of a laser printer. Now, let us see the working of a laser printer. As you can see here, the laser source produces a laser light which consists of information in the form of light, and that light falls on a mirror, and the mirror reflects back on a photosensitive material like aluminum drum, where wherever data is there, that part of the material or that part of the portion will be charged with positive. As you can see in this animation, once the drum rotates, the tuner will dispense the fine particle which has positive in charge, negative in charge. That negatively charged particle is attracted towards the positively charged particle, and that particle is placed on a paper, as you can see here. Once these particle placed on a paper, fusing section will produce external heat and pressure to paste or fix that particle on a paper. This is the working of a laser printer. The last application in this chapter, that is laser cooling. Before we are going to start with the laser cooling, I need to confess you one thing. There is no working model available for laser cooling technique. We have theoretical explanation, but we don't have any working model. So to understand in better way, I am trying to generalize the concept by taking simple example. For that, let us take one simple thing. When a metal start heating, as you can see here in the diagram, the metal start heating. Due to this reason, the molecules which is present inside that metal start vibrating with a certain frequency. What is that frequency? It depends on the amount of heat transferred to that material. If we increase the temperature of that material, the frequency of vibration also increases. If we decrease the temperature of the material, the frequency of vibration also decreases, as you already know this concept. Now, by considering this one, let us take one simple molecule which has higher frequency of vibration. That means this molecule has more temperature or more energy. Due to that reason, it's moving randomly in all the direction with the higher frequency. To control, to contain the motion, we use laser light in all the direction. Due to this reason, this molecule reduces its frequency. Now, the word reduces frequency, higher frequency. That indicates whenever higher frequency is there, the temperature of molecule will be more. Whenever lower frequency is there, the temperature of molecule decreases. So, how much decreases? Only in terms of millikelvin, nano Kelvin or micro Kelvin. This is how laser cooling techniques works. In this process, we have two types of cooling. One is Doppler cooling, another one is Simpson's cooling. So, this is the laser cooling technique. By this, we came to end of this chapter, that is called laser. So, if you like this video, please subscribe to my channel, share with your friends to help them to understand physics very easily. See you in next chapter.